Welcome to you all for this session. In this session, we are going to study Stokes' treatment of reflection and transmission at an interface. First, let us understand this diagram. Here, in this diagram, it has a denser medium, that is glass medium, and a rarer medium, that is air medium. Refractive index of air medium is 1 and refractive index of glass medium is 1.5. Here, light rays are incident from this glass medium. If we look into this particular ray, this ray is traveling from denser glass medium to rarer air medium. At the boundary, that is interface between air medium and glass medium, this ray is reflecting, and again at the interface separating air medium and glass medium, it is reflecting and transmitting into the glass, that is denser medium. Here, when this light ray is reflecting from the denser medium, then the light ray will undergo a phase change of pi. And if you look into this particular point, again here also light is reflecting from glass medium, and again it is going a phase change of pi. Now look into this particular part. Here light is coming from denser medium and entering into the rarer medium. At this boundary, the boundary between air medium and glass medium, it is reflecting. Therefore, it undergoes a phase change of 180 degree. But if you look into this particular ray, the rays coming inside the denser medium, inside the glass medium, and it is reflecting from the air medium. If it reflects from air medium, then this ray will not undergo any phase change. That is, there is no change in the phase. Light ray undergoes a phase change only when if it reflects from the denser medium. The statement of Stokes' law is, when a light wave is reflected at the surface of an optically denser medium, it suffers a phase change of pi or a path difference of lambda by 2. But no phase change takes place when it is reflected from the surface of the rarer medium. Okay, now let us take a rarer medium and denser medium. Rarer medium and denser medium are separated by an interface PQ. Let AB be the incident light wave, and the incident light amplitude is A. This incident light will reflect and also refract or transmit through this denser medium. Part of light will be reflected and part of light will be refracted. When light ray reflects, let R be the coefficient of the reflected light. If light ray transmits, let T be the coefficient of transmitted light. So here AB is incident light wave, BC is reflected light wave, and BD is transmitted light wave, light ray. Amplitude of reflected wave BC is equal to AR. Amplitude of transmitted wave BD is AT. When there is no absorption of light energy, then we can write R plus T is equal to 1. This reflected and refracted or transmitted light rays can be reversed. That is, when the reflected and refracted waves are reversed, the resultant should have the same amplitude A as that of the incident wave. When the direction of BC is reversed. In this diagram, let us reverse the direction of BC. When it is reversed, part of light will reflect and part of light will transmit. When light is traveling from rarer to denser medium, R and T are the coefficients of reflected and transmitted light. Here amplitude of this incident light is AR, therefore amplitude of reflected light is ARR. Amplitude of the transmitted light is ART. This BA is reflected light, BE is transmitted light. Similarly, when the transmitted light is reversed, if light travels from denser to rarer medium, let R dash be the coefficient of reflected light and T dash be the coefficient of transmitted light. Here BD is the incident light, its amplitude is AT. This light will be reflected. Some part of light will reflected in the same medium and some part of light will be refracted in the another medium. The reflected light BE is having, or can be written as, amplitude can be written as ATR dash, and amplitude of the transmitted light can be written as AT dash, because it is incident light amplitude. So from this diagram, amplitude of reflected wave BE is AT dash and amplitude of transmitted wave BA is equal to AT dash. I will combine these two. When the light BC is reversed, we are going to get this diagram. When light BD is reversed, we are going to get this particular diagram. Combining both the diagrams, we are going to get this diagram. So I am adding both the amplitudes, ARR plus AT dash, and here ART plus ATR dash. AR is amplitude of the wave CB and AT is amplitude of the wave BD. Now let us compare this resultant diagram with the initial diagram. So here we can clearly write that two amplitudes along BA will combine together to produce the original amplitude A only if the resultant amplitude along BE is 0. In this diagram there is no amplitude. Amplitude is equal to 0. Just by comparing both the diagrams, we write ARR plus ATT dash is equal to A, or AR squared is plus ATT dash is equal to A, and ART plus ATR dash is equal to 0. From this diagram, this can be rewritten as R is equal to minus R dash, where R is coefficient of reflected light in rarer medium and R dash is coefficient of reflected light in denser medium. This can also be written as R dash is equal to minus R. Here we have AR squared plus ATT dash is equal to A, and this is equal to 0. Therefore R dash is equal to minus R dash. Here the equation 2 shows that the coefficient of reflection in both the media are equal in magnitude but opposite in direction. That is, there is a phase change of pi. But the equation does not give us any information that which reflection suffers a phase change. According to the equation 2, there is a phase change of either at reflection from denser to rarer medium or at reflection from rarer to denser medium. This was experimentally confirmed by Lloyd that reflection of the light wave from the surface of the denser medium suffers a phase change of pi, while the reflection from the rarer medium does not suffer any phase change. Thank you.